Welcome. So today we're talking about inodes. Also, we'll leave a bit of time because there's TA evaluations the department wants. So we'll leave a bit of time for that as well at the end. So let's get talking about inodes, which we left off at talking about indexed allocation and how that could be pretty good, but our file sizes we could support are only something like 16 megabytes, which isn't that great. So what an inode would do, and this is the predominant data structure in the kernel when it comes to file systems, that's where all the information about the contents of a file actually lives. So that's where the mode is stored for a file, and the mode is all the permissions. And then there's space for the owners, which is a user ID for the user that belongs to, and then the group that belongs to. And then there's some timestamps to keep track of when a file is created, accessed, and modified last, which you could, of course, change at will. Then there is a field for the number of blocks that this file occupies. And then there are a bunch of pointers to point to those blocks that the file occupies. So there is a bunch of pointers. There is some pointers that point directly to blocks, in which case you should use them directly, and that's as an optimization for smaller files. So if a file only takes up a few blocks, well, it doesn't need to use a block for all the indexes. It can just point directly to the blocks that it occupies. And then there's a field for single indirect, which was our idea for indexed allocation before. So that's to represent, bigger files than the smaller ones, but still not that big. So a single indirect block points to a disk on the block, or a block on the disk, and then that block contains all of the index nodes, so it just contains a bunch of pointers. And then similar to how we have multi-level page tables, well, the same idea applies to files. So there is one pointer that should be treated as a double indirect block. So that points to a block that are full of pointers that point to another block that are full of pointers that then you can, that then point to blocks. And then finally, to support even bigger massive files, there are triple indirect blocks, which is like a 3-level page table. So it points to a block, which points to a block, which points to a block. And then all those have the index bits that actually point to the actual blocks on the disk. So any questions about that? It's the same idea as page files, except now, instead of just having, on our page system, we just had 3 levels and that was it. Here we have a varying number of levels depending on how big the file is. So if it's little files, we don't have to worry about that. Then for slightly bigger files, it just points to a single block, which is full of pointers. And then we have the double and then triple indirect ones for larger files. So the goal of this is to be efficient for small files and also support large ones. So the inodes will hold all the metadata and pointers to blocks, and we'll see how this comes into play when we look at files. So if you're a smaller file, you don't have to consume space for pointers. They're just stored directly on the block. But larger files would have to follow the blocks depending on which one they use and how big they are. So there's also a small optimization here where if it's a very small file, it can actually hold its contents directly on the inode itself. So here, there's like a number of direct blocks, single direct, double indirect, and triple indirect. Typically, you will have 12 direct blocks and then 1 single indirect, 1 double indirect, and 1 triple indirect. So you'll have 15 pointers. And if they're each 4 bytes, then you have 60 bytes of information. So one of the optimizations is if your file contents are less than 60 bytes, I don't need to point to any blocks. I can just use that information and store the contents of the file directly on the inode itself without having to waste any more blocks. So given that, now we can figure out how big of a file we could support. So this is the scenario I was talking about before for an inode. So it could store 12 indirect blocks, one single indirect, one double, and then one triple. So given that, and then each block is 8 kilobytes in size, a pointer to a block is 4 bytes, and indirect blocks only consist of pointers only, so it's however many pointers you can fit on a block. So now we can answer the question, well, under this scheme, what's the maximum size of a file indexed by, that can be represented by this inode? Well, it's the same thing as last time. We still have the same number of pointers that we can fit inside of a block, so that is 2 to the 13 divided by 2 to the 2. So we can fit 2 to the 11 pointers on a block. Then, if we want to calculate the total number of addressable blocks, well, in this case, we have 12 blocks that can be directly addressed just from the inode itself, because those are the direct ones. And then for a single indirect block, it would point to a table, and that single table could hold 2 to the 11, because that's the number of pointers. And then if we had a double indirect block, we have to take 2 to the 11 to the power of 2, because each entry points to another table. So it would be 2 to the 11 to the power of 2. And then for triple indirect blocks, it would be 2 to the 11 to the power of 3. So instead of adding all these numbers together and having a not nice power of 2, we can just estimate it to be the largest one, since that'll probably dominate the size of all of them. So 2 to the 11 to the power of 3 is going to be 2 to the 33. So the total number of bytes that we could hold in a file would be 2 to the 33 blocks times how big a block is. So a block is 2 to the 13, which would mean the maximum file size we could have is 2 to the 64, which would be 64 terabytes for a single file. So that's more like a file system we would have nowadays, and this is the actual structure the kernel uses. So your maximum file size, there is a maximum, and it's 64 terabytes for a single file. It'd be slightly over this because we did an estimate, so you could have this many more blocks, but ballpark, it's about 64 terabytes. So so how files get represented are the entries in your directory are not the actual files themselves. Every entry in a directory is just a pointer to an inode. So it just records the inode that represents whatever file that is. So your to-do.txt, if you have it somewhere on your drive, it looks like it's in a folder. Well, if you know the structure of the file system and how Linux works, to-do.txt is actually going to reference an inode, which will be some particular number. So in this case, assume to-do.txt points to inode 1. That would contain all of the contents of the file. So that would contain the metadata, what blocks it points to, all its permissions, and things like that. And within a directory, all it would record is the name and what inode it points to. So the directory, a directory doesn't have that much in it. All it is pairs of name to inode, and that's it. So hard link points to one inode, and typically this is the case if you have a file that you just create, it points to one inode and nothing else points to that inode. But what you can do is create something called a hard link. So multiple hard links can point to the same inode if you know what to do. So to-do.txt and b.txt can point to the same inode. And when you remove that file, it only removes the hard link. And that doesn't mean that content of the file is actually deleted, because something else could be pointing to that inode. So POSIX only has an unlink call, and that's what unlink does. All unlink does is remove this, like if you did rm b.txt, well, there's no actual remove system call. What's going to happen is there's going to be an unlink. An unlink would just remove b.txt. So now b.txt is no longer pointing at inode 1. But since to-do.txt is pointing at inode 1, well, it's not going to actually be deleted. So then there's something called a soft link. So a soft link, all that does is point to the name of another file. It doesn't point to an inode, it just points to a name. So when resolving whatever file that is, the file system is redirected somewhere else, and it reads that content. So if I have create b.txt as a soft link, instead of pointing to an inode, it just points to a name. So it could point to something like todo.txt. And if you want to read the contents of b.txt, well, you have to know from b.txt, you have to follow it to todo.txt, and then you can get the inode and then actually figure out the contents of the file. So we can see when we play with this too that sometimes soft links, the targets can be deleted. So we could delete todo.txt, and then you can't resolve the target of a soft link, although it still exists. And that would be a condition you have to cover in your programs that, hey, the files I access might actually be soft links, and they might not actually point to somewhere. Yep.
So would soft links be equivalent to shortcuts in Windows?
Yeah, soft links are essentially like shortcuts in Windows. So they just point to a name, point to a path. So if you in Windows, if you have a shortcut and then you delete whatever that's a shortcut to, then your shortcut doesn't work anymore. So same idea is here, it's just the Unix-y way of doing something. So let's take this example so we can play around with this and see what would happen. So in this, say we touch todo.txt, and all touch does, if you haven't seen it before, is it just creates a new empty file. So if we look at our directory, we just have one file in it called todo.txt, and now we can actually expand our skills a little bit. So we know ls-l to show kind of more columns. So over on the left here are all the permission bits, and then here is the number of links, which we didn't know before, and then that is the user that owns the file, the group that owns the file, and then the date modified and all that stuff. So if we add in a I, well, we get a new column here. And that new column all the way to the left is the actual inode number that todo.txt points to. So what we can do is create a hard link. So has anyone used ln before, like -s? No? Okay, so ln-s is how you make a soft link, but we'll see that in a bit. If you just use ln, that creates a hard link. So if I do ln, the first argument is a hard link to what? So this is a hard link to whatever todo.txt, whatever inode todo.txt is. And I'm going to call the new entry into the directory b.txt. So if I create this, whoops, I hit a bad key. If I create this, then I have a file called b.txt. And now if I look at it through this, I can see that the number on the left column is the same. So they have the same inode. So if I go ahead and edit todo.txt and say hello, so I save it. Now if I cat it, what should I see? Hello, hopefully. So I can cat it and say hello. But now, what would happen if I catted b.txt? What should I see? Any guesses? Hello? Oops. Yeah, so if I cat b.txt, I see hello because they're actually pointing to the same inode, and the inode points to the contents of the file. So I can access that same inode through todo.txt or b.txt. It doesn't matter which, right? I could edit b.txt, edited from b. So if I go ahead and edit b.txt and then just look at todo.txt, well, I can see that it's actually the same contents of a file because it's the same inode. So I can edit it directly. So the other thing we could do is create a soft link. So it's the same, works the same way as creating a hard link, except you just use -s, and that means it's a soft link. So I'll create a soft link to the name todo.txt, and I'll call this c.txt. So if I go ahead and look at the directory again, well, I'll see that there's this new entry called c.txt. I should move myself out of the way. So I see this new entry called c.txt, and c.txt, oops, here I can increase it. So c.txt, you can see it just points directly to todo.txt, but all the way on the left here, it's actually a new inode. But because it's pointing to todo.txt, if I cat c.txt, well, it will just magically go ahead and resolve that. So it knows that c.txt is a symlink, so it would go ahead and access todo.txt instead, and then get the inode from todo.txt, which would then lead us directly to the contents of a file so we can display it. So the other thing we can do is we could, now if we move todo.txt to something like d.txt, well, all that does is change the name of todo.txt. It doesn't change anything else. So if I do an ls again, I can see the d.txt, well, it was todo.txt. Move just simply renamed it. It didn't actually move anything, unlike its name. So its inode is exactly the same as it was before. I just changed its name. And now we can see in red that I broke the soft link. So the soft link isn't guaranteed to exist or point to anywhere that you care about. It's just a name. So c.txt just has an entry that says, hey, I point to todo.txt, and now I don't have anything named todo.txt anymore. So if I try and cat c.txt, well, I'm going to get no such file or directory, which is a really confusing error because c.txt exists. So that's not my problem. So you might, if you don't know what a soft link is, you might get that error and be like, well, that's stupid. c.txt obviously exists, but what it's trying to tell you is the thing that c.txt points to doesn't exist, which is a bit of a pain. So, and then finally we can go ahead and remove b.txt, which of course removing b.txt doesn't change, just removes that entry that points to that inode, but I still have something else that points to that inode, that d.txt. So my original contents that I edited before are all still there, even though I moved around to do.txt and changed up and deleted one thing, which didn't actually delete anything. It just removes entries in the directory. So any questions about that fun stuff? Cool. So if you were to write out what the file system looks like before and after the remove commands, well, it would look something like this. So before the move, we created todo.txt, which would have created its own inode. And then we created a hard link where b.txt points to the same thing as todo.txt, so they would both point to the same inode. And then c.txt is a soft link to todo.txt. So hard links point to inodes, soft links point to other names. So before the move, this is what my file system looks like. And then after the move, all I'm doing is renaming todo.txt as d.txt, so it's pointing to the same inode. I just changed its name. But now c.txt is pointing to a name that no longer exists anymore. So you could put it in black to say that, hey, it doesn't exist anymore. And then if I remove b.txt, all that happens is I just remove that name in a directory. So the name b.txt no longer points to that inode. So in Unix, everything is a file. So directories are just files of type directory. There's additional things. So files can be a regular file, which is what you're used to. A block device, which means you can only access it in big blocks. So that represents like a hard drive or an SSD, something like that. We've seen pipes and we've seen sockets before. So just so we know, directory inodes do not store pointers to data blocks. All it stores are file names and pointers to inodes. So it's just a bunch of tuples that are just file name, inode, what are they all? So looking at that too, let's go back to our example here. Let's recreate that hard link. So I'll create a hard link to d.txt called b.txt again. So if I do that, two things point to the same inode, and then if you want to read the contents of an inode, well, there's a stat system call and also a stat command you can run. So the stat command will tell you a bunch of information about what you just accessed and then what is specifically on the inode. So this is the file to b.txt, which that's gotten from the directory. And then the rest of the information is the inode itself. So it is 22 bytes large. It occupies 8 blocks. My IO blocks are 4 kilobytes. It's on some device. So, and then its inode number, and then it actually keeps track of the number of links there are to it. So right now there's 2 links. There's b.txt and d.txt. So it keeps track of that information on the inode itself. So the kernel actually knows when it can delete the inode. So the kernel can only delete the inode if there are 0 things pointing to it. As long as there's 1 thing pointing to it, it can't actually delete it. And when you RM it, you don't actually know if it's deleted unless, ahead of time you check that there was only 1 link to it before you deleted it. So then you can see the access, the user ID, the group ID, and then all the access modify change timestamps. And there's also a birth timestamp as when I created it. So if I go ahead and say I remove d.txt and I stat b.txt again, well, now I can see that my number of links decreased from 2 to 1. So I'm 1 step closer to being able to actually delete it if I'm the kernel. So any questions about that? So after that, we should have a good understanding of what's kind of stored on the inode itself. So the file name is not stored on the inode itself. That is only inside the directory because the directory keeps track of names to inodes. An inode itself has no idea what its name is. It doesn't really care. So also to that, it doesn't know where it is contained because it could be contained in multiple places at once. It would know the file size. It would know the file type. An inode would also not know the number of soft links to a file because you'd have to follow a bunch of links from the directory and it just doesn't care. So consequently, it would not know the location of the soft links. It would know the number of hard links to the file, so we saw that in stat. So it knows how many hard links are to it, and the kernel has to maintain that number to make sure it is correct. But it's not going to know the location of the hard links. So knowing the inode, you have no idea of what is actually pointing to you without actually traversing the whole file system. So there's no way to go backwards from inode to a bunch of names. But other things it would have on it that we saw is it has the access rights or permissions. It has the timestamps. It doesn't store the file contents. It points to blocks of the file. Although sometimes, if it is optimized, it can sometimes have the file contents if it is actually small enough. And then lastly, it would definitely have an ordered list of data blocks because that is the whole reason we have this inode structure in the first place. So here's the answers to all of that. So again, C is because the file contents, if they're small enough, will sometimes fit on the inode itself. So I can go ahead and verify that and show you. So usually the number of blocks that are associated with the file, it will tell you if you stat it. So let's see in here. In here, I see a c.txt, which points to to-do.txt, but I can stat c.txt and see the actual contents of the inode itself because it's its own inode. So if I look at that, I can see it knows it's a symbolic link here, but curiously, it is pointing at 0 blocks. So it's not actually consuming any space on my hard drive. So, and the size of the file is only 8 because because it just holds the content of what it points to. So its size is 8 because to-do.txt is exactly 8 bytes long. So all it holds, so that shows that it only holds the contents of, it only holds the name of what it points to, and that is the only thing it contains. So what the optimization here is, because size is 8, well, usually in the inode itself, well, these are all 4-byte pointers. And then we're going to have something like 12 direct, 1 indirect, 1 double indirect, and then 1 triple indirect. So if we add all that, this means we have 15 pointers, which would also equal to 60 bytes, since each pointer is 4 bytes. So the optimization is if the size of the file is 60 bytes or less, it's not going to store anything. It's not going to store any pointers because it can actually fit in the 60 bytes. So I reuse the space that I would have for pointers, and I actually put the contents of the file there. So in this case, if it's a symbolic link, well, the only thing it contains is the name to-do.txt. So the first byte would be the character T, then O, then D, O, dot T, X, T. So I would reuse the space for the pointers and just put in the string that the symlink points to. And that is the whole thing. So that's a good optimization. Otherwise, the file would have to take up at least 1 block. And if my file is only 8 bytes long and my block is 8 kilobytes, I'm essentially wasting 8 kilobytes every time I make a symlink. And usually your symlinks, the names they're going to refer to, are going to be less than 60 bytes. So this is a worthwhile optimization. So any questions about that? Okay, so that's pretty much it for inodes. So the file system will, again, like we talked about before, use a cache to speed up writing to disk. So we know that writing to a disk is slow, and like always, we'll use a cache to speed it up. So what you can do is cache file blocks and cache them in main memory, and that would be something called a file system cache. And then you would create the cache because, well, you know that if you reference a block, it's likely to be referenced again. If that file represents something like a database or something like that, you'd constantly be revising entries and modifying them. So that would also be an example, like we saw before, of temporal locality. And then logically, blocks are near it are likely to be referenced next. So things could be spatially located. So if I read a file sequentially, well, I know that I'll be reading the next contents of a file. So one optimization you could do if you are the kernel is go ahead and preload that information into your cache. So it's there just in case something uses it. And then you could also use that file system cache to record writes to. So you could record all the writes to memory and not write them out to disk until as late as possible. And that is why there are special system calls to actually trigger writes. So there is a flush and a sync system call, and that actually triggers that file system cache to actually be flushed to disk, so you know for sure that you're actually going to have that information written to the disk. So if you lose power or something like that, then you actually don't lose data. So one of the last things about file systems are something called journaling file systems, which are file systems that try and ensure some integrity. So now we know all the steps you have to do if you want to delete a file on Unix. So deleting a file, assuming that's the last thing, last reference to the inode, involves 3 steps. So I remove its entry from the directory, and then I would decrease the number of counts to that inode, and if it's 0, then I would release that inode to the pool of free inodes, and then as the 3rd step, I would, whatever blocks that inode was pointing to, I have to set those all to free now because other files could now use that because I'm no longer using it, so I should return it to the pool of free disk blocks. So if you actually care about data integrity, well, a crash could occur between any of these steps. So say we crash between step 1 and 2, well, that inode would still look like it is in use, and all the blocks it would point to are still occupied. That inode also is still occupied, even though nothing actually references it anymore. So we would lose some information there that we'd never be able to get back. And similarly, if it crashed between steps 2 and 3, well, that inode would be released so it could get reused, but now all the blocks it points to are going to still appear to the kernel as being occupied, even though that they're free. And since we can reuse the inode now whenever you power the machine back on, well, all those blocks are going to be lost till the end of time. So that would give you a storage leak. And what a journal does, it basically just contains all the operations in progress. So if a crash occurs, you can recover. So the journal would write an entry before it starts those 3 steps that says, hey, I'm going to remove this entry in the directory, and be like, okay, I'm starting it now, and then go through the steps. And only after it's done, it would remove it from the journal. So if it crashes, it would still be in the journal, and then you can retrace your steps, and then knowing how you do the steps, you can see at what step something broke down. So that's the point of a journal. So if it powers off any time between there, you can recover because you know what operation crashed, so you can go ahead and actually release the blocks or something like that if that's the step it crashed on. So inodes were the hybrid allocation strategy, so they offer way greater flexibility over contiguous, linked, fat, or indexed. It's basically indexed, but we're taking an idea from our page tables, and everything is a file on Unix. Names in a directory can either be hard links or soft links. Hard links point to an inode, and soft links point to a name. So we'll take the rest of the time to do the TA stuff, and just remember, I'm pulling for you. We're all in this together.